Thank you for talking. My first class, no one talked at all. So I prefer this. I prefer social atmosphere as long as we're on points, focused, and working hard. Because you will have to in this class. It is difficult, okay? It's a difficult class, but it's the best. It's the best. It's super cool. So I hope you enjoy it. Get ready. Okay, so syllabus isn't ready. Canvas homepage is not ready. But the first homework assignment is ready. So I'm going to, in the next day, I'll have all the intro stuff. But this is the basic stuff that's from the first page of the syllabus. Those office hours are direct. I'm going to go for Monday, Wednesday, 1 to 2:30. And the best way to contact me is always email. Am I recording? Yeah. Best way to contact me, always email. And then you can try calling my office, which is right there, right across the street from the bookstore and the Computing Commons. It's ECA. And so you can try calling, but never leave a message. We never check those messages. So email is the best way to contact me quickly. And then the textbook is recommended. It's not required. It's more like a reference. And then I'll be posting like practice problems for the exams from like some review exercises. But I'm not. The homework is all on WebWork. It's all online on WebWork. So textbook recommended, but you can make it through the course without the textbook if you're smart, I guess. I don't know. But I don't know. So I don't know how much past students have used the textbook in the way that I'm teaching the class. So I don't know. So you can decide whether you want to have that as a reference or not. All right, and then a calculator, just a standing graphing calculator will work. Any questions about the basic stuff? Yeah. No, you won't have, like in 271, you don't have a copy. We're not using, I don't have assignments for you for GC. I'm going to be using it extensively in class, but it won't be part of your homework like it is in 271. Okay, other questions? But if you still have a copy, it's amazingly helpful in this course because you can render everything in 3D, and then you'll see me doing that in class. So I encourage you to keep using it, and if you need me to help you show you how to use it in office hours, and definitely hit me up to make use of that in this course. I mean, I should structure this course around GC for you guys. I just haven't had the time to do it yet. So I highly encourage you, if you have a graphing calculator on your laptop, to apply it to this course and please contact me for help with that. Other questions? Okay, so let me just show you the if you go to webwork.asu.edu, you'll see something like this. Oh, so if you just let's go. All right, so this is what you'll see. Webwork.asu.edu. Write that down. You have an assignment due Wednesday morning. So if you've not done this before, write that down. And then you're going to go to 272, which is lower left corner. Click on Ashbrook. And then you will see after class, this won't say, no longer will say will open. It will say opened. It opens at 12:40. So you're going to click on set 1, vectors in R3 intro. And then you have 19 questions. Many of these are shorter type questions, so don't let that scare you too much. And you're working on that tonight and tomorrow night, and that's due, I'll make assignments due 11:30 a.m., the next class. In pretty much every class, there's a WebWork problem and a WebWork set. Just expect that. And then once a week, you'll turn in a written assignment, which will be problems that you start to work on in recitation, and you'll do a formal write-up and turn those in a week later. Okay, so WebWork every single class, do 11:30 a.m. before class, and then no, I take that back. I'm gonna switch that to like 5 p.m. the next day. So I'll switch this. The deadline will be 5 p.m. on Wednesday, so that we can tie up any loose ends in class Wednesday, and you have a little more time to work on it. So it will always be due 5 p.m. after the next class. Okay, so this one I'll change it. Okay. All right, let's jump in. We got lots to cover. So, oh, and I am recording on Canvas. Once I get Canvas up in modules, I'll have there'll be a module for exam 1 content videos. Okay, and so then I'll have a screen recordings from class posted there, and those are for review and reinforcement, not for skipping class. Class is absolutely essential. Okay, so the deal with it though is you have so many other things going on in your life that you can leave class with a 98% understanding of what we talked about, or even 90%, and you're like, yeah, I got this. But after you go home and you do your laundry and you go to another class and you eat a cheeseburger and then you go play ultimate frisbee and then now all of a sudden we're at 40% of what we learned, right? So when you're learning things the first time, they fall out of your brain quickly. So that's what the videos are for. Later that night, the next day, review the video. You can pause it, take really good formal notes. Think again through what we talked about, and this is when the retention starts to happen, right? This is by repetition. We learn and understand through repetition. So that's what the class videos are for, and those are found in modules on Canvas. Okay. No. Okay, so let's jump in. So it would not be wrong to call Calc 3 a course of vector calculus. There are other names that wouldn't be wrong as well, but one name for Calc 3 would be, it's a course of vector calculus. So we better know about vectors. That's how we start the course. So to understand a vector is to know what it means compared to a scalar. So a vector, so scalars are mostly what we've been dealing with through Calc 1 and Calc 2. Quantities that have magnitude and not direction. Or maybe they had direction, but we weren't really thinking about the direction. We were just thinking about the magnitude of the quantity. So when I say quantity, I mean distance, speed, temperature, volume, area. Okay, that's what I mean by quantities. Things that you can measure, right? Attributes that you can measure. So, and then vectors, so what are some examples of that? What are examples of scalars? Quantities that don't have direction associated with them. So I've already put one up there, temperature. What else?
Density.
Density is a good one, right? Density is just a magnitude. It doesn't have direction. What else? Yes, pressure does not have direction. But the thing that has direction related to pressure is what has so pressure is non-directional. But when you kind of force then is kind of the related quantity that has direction with it, right? So force would not be scalar. Any other scalars you can think of? Yeah, charge is a scalar. So mass is a scalar. Time elapsed doesn't have a physical direction associated with it. Volume, those are all good examples of scalars. So vectors then are quantities that have a direction associated with them. So we said force was one. Can you think of another one? Besides force, what else? Yeah.
Speed.
Okay, velocity. Yeah, velocity. Acceleration. Okay, so force, momentum. All right, so displacement. Okay, displacement. What displacement means is a change in position. So if I start here and I end up over there, do you see that has a magnitude, right? How far? But then it also has a direction. Okay, so just the scalar, the magnitude of displacement then is distance. So we're just defining terms here. When we say displacement, we're talking about a vector quantity, how far and in what direction. When we say distance, we don't care about direction. It's just a scalar, how far. Does it make sense? And so then we have the same thing when we talked about velocity as a vector. And what's the scalar associated with velocity? When we don't care about direction, that's speed, right? So velocity means how fast and also in what direction. That's the vector. And then just the how fast part, regardless of direction, that's what we call speed. Okay, questions on just what a vector is, right? It's a quantity that has an associated direction with it, where scalar has no direction. Okay, so how do we represent them? We use arrows. So we use arrows. And so then the length of the arrow is kind of representative of the amount, and then of course the direction that the arrow points is the direction. So the direction the arrow points, the arrow length corresponds to the magnitude. Okay, so the arrow showing the vector has a tip and a tail. So tail is in starting point. So from tail to tip is the direction, right? From tail to tip is the direction of the vector. So which of these A, B, C, or D has the least magnitude? And the greatest magnitude? B. So least magnitude would be C, and the greatest magnitude would be B. If these are all proportional, right? If these are proportional. Okay, so symbolically, you either see them represented as a bold letter, like often like in printed text, but then when we write, you throw an arrow over the top. So whereas just A might be a scalar, like maybe A is temperature in the room, but then an A with a vector is representing some vector quantity. So that's how you'll write it by hand. But you'll see it also bold like on WebWork and textbooks. Okay, so equal vectors. So a vector has a specific direction and magnitude, like we said, but it doesn't have a distinct location. So we'll say often, vectors are mobile. Vectors are mobile. All right, so force vector. So I can push straight against this wall with 30 pounds of force. But if I come over here and I push straight against this wall with 30 pounds of force, it's a different vector or the same vector? Same vector, right? But if I push on this wall with 30 pounds of force, same vector, different vector? Because? Different direction, right? So if it's in the same direction with the same amount, it's the same vector. So 5 people move, starting at different places and times. They all go the exact same distance, heading in the same direction. What kind of vectors are these? What do we call these? No, but what quantity is this that we talked about? Displacement. These are displacement vectors, right? They're showing distance and direction, so they're displacement. So these people all start at the tail, and then they end up at the tip. And since they all have the same distance and direction, they're the same vector. So they just call them all just D. You don't have to distinguish between those. Those are all the same vector, D. Oh, sorry, I wish the screen came down lower, or maybe. That's just showing that D1 equals D2 equals D3, and they all equal to D. That's what's missing there. It's going to be a problem. Some white paper. Okay, so those are equal vectors. Okay, adding vectors. So adding vectors, the easiest way to start thinking about adding vectors is with displacement vectors. So let's just consider these displacement vectors. And so to represent the addition of vectors, we're going to place the arrows tip to tail. Tip to tail. So vectors are mobile. So I can take vector A and I can put its tail on the tip of B. Did you see that? Watch this. So, right? Did I change the vector A? Same vector A. Just I put its tail on the tip of B. And so if we think of these as displacement vectors, it's like we started at home, and then we walked to Walmart, and then we walked to McDonald's. And so what's the overall result of that? If you put those two together, right? If you add them, you put them together, what's the overall result? The overall result is that I started where? Home, and I ended at McDonald's, right? So adding those, it's the sum of the sum is the single vector that gives the same outcome, like from tail to tip. So that would be B plus A would be the blue one. That's B plus A. So you can think of it as like the sum of vectors is like as the crow flies, right? So if you do a zigzag course, the sum of all those vectors is how the crow flies from your starting point to your very ending point. That's what adding vectors is like. So what about A plus B? So now I do A first. Is that the same vector A or a different vector A? Same vector A? Same vector B or different vector B? Same vector B. But now I'm going to do A plus B. So I take the tail of B and put that on the tip of A. And so now I'm doing A plus B. And what do you notice? Same as B plus A, right? You see that A plus B is the same vector as A plus B is the same vector as B plus A. Same direction and magnitude. So with vector addition, like scalar addition, it's commutative. You can change the order and you get the same vector. So vector sum is the same. A plus B equals B plus A. Any questions? Okay, subtracting vectors. So we can start thinking about by adding the opposite vector. So if I want to do B minus A, so what would adding the opposite of A, what would the opposite of A be? Yeah, so opposite of A would have the same magnitude as A, but then it would be in exactly the opposite direction. So the opposite of A would look like that. And then we do B minus A, so I'm going to put the tail of, so B plus the opposite of A means move the tail onto the tip of B. So B plus the opposite of A is B minus A. But this isn't really the way that we do vector subtraction visually normally. So that's a good starting point. That's true. That works. But normally with subtracting vectors, we do them tail to tail. So normally you start subtracting vectors by putting them tail to tail. So we know that the resulting vector is going to finish the triangle, so then the question is what direction. So when you do the tail to tail approach, you finish the triangle, that's going to be, but then you have to figure out which direction. So there's a couple of different ways to do that, to figure out which direction. But we already know it. We already know what the direction is because we did it by adding the opposite, okay? So there's a couple different ways to figure out what direction the difference is after you complete the triangle. And the one way you can do that is you can check with addition. All right. So looking at those three vectors, how do you see that as a vector addition? What plus what should equal what? So do you see here we're tip to tail right here? So therefore, what addition problem is this representing? A plus B minus A equals B, right? So does the math work, right? So if you're just looking at those, A plus B minus A, well, you get A minus A goes away and you end up with B. So the math works. Do you see that? So that's a way you can do it. You can try the direction both ways. What's that? It's as far as it goes. I tried. All right, I'll just write it out. Here we go. So what that says is check with addition. So A plus B minus A. So does the math work out symbolically? A minus A goes away equals B. So had we guessed, say, I didn't know from this problem, I didn't know, and I was just kind of guessing. So I come along here and I go, I think I want to just try this, right? So then what addition problem would this triangle represent? Where is it tip to tail here? Oh, I just need to do. There we go. Okay. So here's my tip to tail. So this would be B plus B minus A. I'm speculating that B minus A. And if it's correct, it should equal A. Does it? It's wrong. So, right. So I'm doing B minus A, and I'm speculating that it goes this way, and so then I'm setting up the vector addition problem to check it. I'm checking what I've conjectured. So the addition problem would be that B plus B minus A would equal A. And is that correct or not? No, because what do you get over here? You get 2B minus A. You don't get A. So that would tell me that conjecture was wrong. It must be the other way. And that backs it up. Okay, does it make sense? So tail to tail, you know the vector difference is going to finish the triangle. It's got to figure out which way. This is one way to check it. You can just like do trial and error. Another way is to think what B minus A, kind of like it's a difference is like amount of change, right? And amount of change is kind of like your final amount minus your initial amount. So do you see how that matches up with the picture? Final minus initial. So if it's B minus A, it's kind of like here I am in the end minus where I started, right? So that's another way to see that it points this way. Final minus initial, B minus A. Okay, so that's a couple of ways to figure out which way the vector, the direction of it, given the tail-to-tail approach, which is what's more often used. Okay. Did that make sense, that explanation? Okay, let's move on. Okay, so vector components. Vectors are most conveniently expressed by their horizontal and vertical components. So it's like we take a vector and we break it down into how much of it is vertical and how much of it is horizontal. And if we add those two components together by vector addition, we'll get the actual vector we started with. Okay, so for instance, here's vector u, here's vector v. And so vector u is showing, if you take vector u and just say, how much of u is in the horizontal direction? Well, it's moving you -1 in the horizontal direction. Right? And then how much of u is in the vertical direction? +2. So those components added together, that first vector that I wrote, I shouldn't have written, this is not good because all I'm labeling here is the magnitude, right? So this is the magnitude of the horizontal component and the magnitude of the vertical component. You add those two components together and you get the vector u, right? Tail, tip to tail. So that horizontal component plus the vertical component gives you the resultant u. And so we can then quantify the vector u as its components, -1, 2. So -1, 2, are those coordinates? They're not coordinates, so then what are they, right? So what is the number -1 and -2? What do they represent? Displacement. So if they're not displacement vectors, but they're any vectors, then what's more general than displacements? Amount of what do you think? So suppose this vector is for any quantity. This is a really key point, that the -1 and the -2 means how much, someone's saying it, change, right? Or variation, right? How much horizontal variation, how much vertical variation in whatever quantity you're talking about, right? Whatever quantity you're talking about. So yeah, so they're not coordinates, they're expressing amounts of variation or amounts of change. All right, so what is vector v then? What are the components for vector v? What does that look like? About. X component is? +4, right? So that vector v has, in its DNA, it has a horizontal variation of 4. And then It also has a vertical variation of -2. And again, I'm kind of doing a no-no here. I'm labeling. I made this PowerPoint a while ago and I never changed it. But I'm labeling the vectors with their magnitudes. You would never do that. I should label them with some other symbols that mean vectors, whose magnitudes are 4 and -2. Okay. So what's the benefit of this is, all right, so another way to do this then is we can express vectors in what's called the unit basis vectors. This is the vector I. What vector is that? What are its components? 1, 0, right? So this is like the unit horizontal vector. It's called a unit basis vector. It's the horizontal, and then that's 1, 0. And then J is 0, 1. So these are called the basis vectors. You can write any vector as a combination of these two scale, right? So we can scale I to any magnitude and scale J to any magnitude, and then add them together to get any vector. So like the vector U would be -1I plus 2J. Right? It'd be -1 in the horizontal direction and then 2 in those verticals. So by adding those two together, you get the vector U, and then similarly V would be 4I minus 2J. And so I could just draw that, so like 4I, so like so you can see that it truly is 4I minus 2J. I could add together 4 I's, and then two negative J's. Right? If I added all those three, I added all 6 of those vectors together, the resultant would be the vector V, 4, -2. So this is adding like 6 vectors together. Okay, so components. So you'll see it both ways, like, right? So when you're doing your homework and in the world and in textbooks, sometimes it will be given in the component form with these what I call chevrons, and then in WebWork, use the greater than sign. You're going to put some of your answers in WebWork will be vectors, and this is the less than sign and the greater than sign to make vectors in components. Okay, but then you'll also see it both ways. So like I had before, -I plus 2J. Both of these are exactly expressing equivalent things, and you'll see it both ways, and you'll have to be fluent both ways. But yeah, so the greater than and the less than sign and greater than sign on WebWork to enter answers and components. Okay, so what am I doing here? Am I doing U plus V or V plus U? This is representing, well, we know that it's the same vector, right? But the representation in the visual is V plus U, right? Because the tail of U is at the tip of V. So it'd be V plus U. And so it's really convenient to have vector components to find the resultant vector, because we can add apples and apples and oranges, right? If we isolate the horizontal direction, then we can simply add amount of variation and get an amount of variation in the horizontal direction. And then if we isolate the vertical direction, we can add those together, oranges to oranges. So what is the vector V plus U? Yeah, so we can add 4 plus -1, and we can add -2 plus 2, because the directions are the same, right? We've isolated x direction, so we can add those quantities, or those values. We've isolated the y direction components, we can add those together. And then you can see clearly that the resultant in the picture is the vector 3, 0, right? Also 3i, right? So that's also 3 times the unit basis vector I. You don't have to write the plus 0j, right? You could, but you don't have to. Okay? So the length of the arrow represents the magnitude of the vector, then we want to find the magnitude of each vector. Okay, I'm going to start taking attendance. So go, you got a little task here, and I haven't told you how to do it, but we're in Calc 3, we're smart, we can do it. So find the magnitude of each of those vectors. I'm going to start taking attendance. Okay, so this is not about something, if you've done this before, it's not about something you've memorized. Figure it out, okay? So hopefully you drew the picture. Pretend you've never done these before. Did you get the right picture? So here's the picture. Make sure you got the right picture. So you're to figure out, like you've never done vectors before, you don't have a formula, figure out what the magnitude of v plus u is, what the magnitude of v is, the magnitude of u. Okay? So it's kind of a problem solving. And so here's the notation for that. When you take a vector and then you put like absolute value bars on it, it's like we don't care. This is saying don't care about direction anymore, just want the magnitude. You'll also see it double bars. Okay? It means the same thing. So you'll see it with single bars like absolute value. You'll also see it like this, double bars. Means the same thing. Okay? You'll see it both ways. All right? So what is the key to finding the magnitude of these vectors then? Or the length of that vector? Pythagorean theorem, that's what you should have come up with. Of the components, right? So it would be, this would be length 1 in the horizontal direction, length 2 in the vertical direction. So it'd be square root of 5. 1 squared plus 2 squared. So that gives us our general formula for if v is the vector, say, AB, then what's our general formula for finding the magnitude of v? Am I still in the white here? Yeah. Square root of, right? So the variation in horizontal is going to be like the leg of the triangle, right? How much the horizontal changes, that leg in the triangle. So it's going to be a squared plus b squared. So what did you get for vector v? Just final answer? 20? 2 root 5? Is that right? Okay. And then now v plus u. Pythagorean theorem? No, you just look at it, right? So you say your brain is active, right? And you say, oh, easy, right? What is it? 3, right? You don't plug this into the formula, or else your brain isn't on, right? You know that all of the magnitude is in the horizontal direction, so it's the 3, the horizontal component. Questions on magnitudes, vectors? Okay, moving on. Okay, sketch v minus u and find its magnitude. So remember, let's do that. So v minus u would mean tail to tail. So I'm going to say move u so that it's up here. Same vector u, I just put it tail to tail. And so v minus u, then with components, again, this is easy because we can just simply subtract individual components because it's apples to apples, change in x, oranges to oranges, change in y. So v minus u, the x component is 5, right? It'd be the x component of v minus the x component of u. 4 minus negative 1 would be 5. And then negative 4. Here's another way to figure out what direction. So I've got my v minus u triangle, right? Tail to tail. Either that's going to point down to the right, like this, to finish the triangle, or up to the left. Which is it? Down to the right or up to the left? Down to the right, because 5, 4 would be a horizontal, a positive change horizontally, and negative change vertically, which would be, so my v minus u would be this tail here, tip here is v minus u, 5 minus 4. Okay, so what about 1/4 of v plus 2u? So now this is bringing into the idea of scalar multiplication. What is the meaning of 1/4 v? So if I have some vector v and I take 1/4 of v, what would that mean? What would that be? What would my new vector be?
You would take 1/4 of each component, right?
Okay, that's, yeah, but like, that's how you get it. But how would it compare to the vector v?
1 and -1, or 1 and -2, 1/2, sorry.
Okay, so that's the math, that's the mechanics of getting it. But what kind of, more of a conceptual standpoint, what is 1/4 of v compared to v? 1/4 of the length, and what about the direction? Same direction, right? So this is what we call scalar multiplication. I'm going to take the vector v and I'm going to scale it by 1/4. In other words, I'm going to shrink it to 1/4 of its size. Okay? And then 2u. And yeah, in order to do that, then you take 1/4 of both the components, right? And so in order to do this, so you get 1 comma negative 1/2, right? That's 1/4 of v. And then 2u. And so how does that compare to u? Twice as long, or twice as much variation, right? Twice as much variation, but same direction. So do you always get a vector in the same direction? When you do a scalar multiplication, do you always get a vector in the same direction? No, you do not. What's the case where you don't get the same direction? If your scalar is negative. If your scalar is negative, what now is the direction? In the opposite. So a negative scalar, it's still parallel. So you always get a vector that's parallel to your original vector. But if it's a negative scalar, you're going to go in the exact opposite direction. And then, of course, scaled by the magnitude of the scalar. And then this is easy, just 1 plus 9 minus 2, negative 1/2 plus 4 would finish this little problem. Okay, so we've got scalar multiplication, we got addition of vectors, subtraction of vectors, vector components, all which we'll be practicing in your web work. So another thing to think about with vectors is that in terms of initial and terminal points. So here's a point P, negative 2, 1, and say Q. These vectors or coordinates? Coordinates. I'm using parentheses, and so these are coordinates, these are locations in the plane. And so I can make two vectors out of this, right? I can make a vector PQ. So if I write PQ and throw an arrow over it, that means the vector whose tail is at P and whose tip is at Q. So I could draw that. and so let's find that, right? So I want to find that vector PQ that whose tail is at P and whose tip is at Q. What would I do? So what is the x component of that vector, right? It's the amount of variation in the x direction. How much does x vary? 3.5. And if these were kind of weird numbers, how would I actually get that? You could see that, so 2 and then another 1.5, so 3.5. But generally, how are we calculating that number? Final minus initial, right? Final x coordinate is? Do you see that's really where that 3.5 is coming from, right? The final x coordinate, the rightmost x coordinate, minus the leftmost x coordinate gives you the amount of variation, right? Similarly, the y component is, how much does y change from P to Q? 2, which is coming from 3 minus 1. Now I also have the vector QP. And we can just write it down. We've done all the heavy lifting here. Because how does QP relate to PQ? Equal and opposite. Equal and opposite, therefore, negative 3.5, negative 2. And again, that would be what? Negative 2 minus 1.5 and 1 minus 3. Final minus initial. So that QP then would be the vector whose tail is at Q and whose tip is at P. Question?
If we drew another vector, let's say you translated that arrow 2 units to the right, would it still be correct to call that vector PQ? Or
Yeah, that's a great question. And yes, because once I've written vector QP, all it is its components. Absolutely. So down here is also vector PQ, even though those aren't points P and Q. But you wouldn't. It's confusing, so you wouldn't do it, right? So you wouldn't do it because it's confusing. But technically, it's still vector PQ because it could be anywhere. Because the only thing that PQ matters about PQ is that it has the components 3.5 and 2, which means it could be anywhere. But I've never seen it done before. I've never seen it. Okay. Other questions? All right, so let's talk about another fair categorization of Calc 3 is that it's calculus in three dimensions, or R3, okay? So far in Calc 1 and Calc 2, we lived here. This is R2, right? Real numbers horizontally, real numbers vertically is R2. So what would R3 be? R3 would be adding another dimension, adding another axis, so that we could represent or orient space, right? Represent or orient space. So here's how we do that. Sit. Get here. So you've got, if you're drawing in your paper, so normally if you're drawing on your notes, you'll do like a vertical axis, and then a horizontal axis, and then like diagonal coming this way, maybe a little bit more down. And so then this is kind of like an isometric view. That should like trick your mind into thinking that's three-dimensional space. Okay, so is this X and Y? No. So how does it work? The way that it works is I'm going to take this x-axis right here. I'm going to grab the x-axis, xy plane. I'm going to pull it like, let's see. I'm going to pull it like this. Okay? So I'm going to grab that plane like this, and then I'm going to set it down this way. flatten it on the table like this, okay? So then that makes, what's this direction then? And then what's this direction? Y. And so then my Z is up. Okay, so again, I'm going to grab this, pull it off, and then lay it down flat. So then my x-axis comes up at you, my y-axis is going to your right, and z-axis is up. Afraid of that. So something like this. So when we have that, we have the x-axis, here's our y-axis, and here's our z-axis. So if I were to plot the point 3, 4, 2, I'm going to come 3 units in the positive x direction. You imagine this coming straight out at you into the classroom, right? So that's 3. 1, 2, 3. And then 4 is then 4 units to the right. So from there, 1, 2, 3, 4. Notice it's not here. It's what? It's here. So you kind of have to draw parallel to your x-axis, so over 4. And then from there up 2. So 1, 2. So this is out in front of the screen. Man, sorry. Is it moving? It's moving. That's why. Sorry. Come on. There we go. All right. So let me do a prettier version of that. So then I can. There's that point. And so making a box is very helpful. Wow, that looks totally different than it does on my screen. That's really weird. Okay. Okay. I think it's distorted. Maybe that's better. Yeah, that's better. Like that. Okay. Gotta go. All right, we're done. Okay, so do as much of there's a lot more to talk about here, but do as much of the web work as you can, and you'll have some time after class, also Wednesday to finish it up.